Hello everyone, and welcome to this first video in a series on approximation theory. In this first one, we'll talk about metric spaces, which is all about how we can mathematically define what a distance is. So a metric space is a set, and we'll call this one A, such that for any two elements of that set, x and y, we can define the distance between them using a function we write as d of x and y, which we use to calculate or describe the distance between them. So this distance function, which is sometimes called a metric, needs to satisfy four criteria in order to qualify as a distance function for a metric space. Firstly, it can't be negative, so there's no such thing as a negative distance, and we write that as d of x and y, or the distance between x and y, is greater than or equal to 0. This can cause some confusion though if we're dealing with negative numbers. So take for example, what is the distance between -2 and -4? Well, if we think of the distance as subtracting one from the other, then we could easily imagine a situation where we take -2 from -4 and end up with a distance of -2. But that doesn't make sense. We know it's going to be a positive number, and often we take the absolute value of whatever we're calculating in order to come up with the final distance. In this case, a sensible distance between them might be 2. Secondly, all the elements in a metric space are unique, and we can write that as the distance between x and y equals 0 implies that x is equal to y. So intuitively, what we're saying is that if we start at x and travel to any other location y in our metric space, then the distance we've travelled must be greater than 0. The distance is independent of direction, and we write this as the distance between x and y is equal to the distance between y and x. So if we draw our 2 points x and y, and we have this green dashed line showing the distance between them, what we're saying is that the distance from x to y is the same as the distance from y to x. So the distance is independent of direction. The fourth and final property of the distance function for a metric space is that the triangle inequality should hold. And we write this as the distance between x and z is less than or equal to the distance from x to any y plus the distance from that y to our original z. And so if we draw a picture of what's going on here, we have our points x, y and z, and if we draw the distance from x to z, we know that this is going to be less than or equal to the distance from x to y plus the distance from y to z. And we know this intuitively. If we're going from one place to another, say I leave work at the end of the day to come home, if we make a detour on that journey, say if I need to go to the shop on my way home, we know we're inevitably going to be travelling further than if we were to just go straight from one place to another. So we're ready to write down our formal definition of a metric space. A metric space is a pair of objects, A and D, where A is a non-empty set and D is a function which takes A cross A and maps it to the real numbers such that d of x and y is greater than or equal to 0, so it's never negative. D of x and y equals 0 implies that x is equal to y, so the elements of the set are unique. D of x and y equals d of y and x, which means that the distance is independent of direction. And finally, d of x and z is always less than or equal to d of x and y plus d of y in z, which we now know to be the triangle inequality.